Hello everyone. Today we are going to discuss about signal to noise ratio, noise factor and noise figure, then equivalent noise temperature, noise in cascade amplifier. So this will be calculated by using Friis formula. So these are all the four topics we are going to discuss in this particular video. So here in the first slide representing signal to noise ratio. For any device, we are calculating the input side input signal to noise ratio and output side output signal to noise ratio. So signal to noise ratio means signal power divided by noise power. So always in a good communication system, every block, every moment we are expecting signal power must be maximum and noise power must be minimum. So this is the actual requirement of any communication system. So here in the communication system, the comparison of signal power with the noise power at the same point is important, measuring the signal power and the noise power. So if your signal to noise ratio, suppose if it is minimum even in the input, then output of the signal to noise ratio will be definitely very low, because if it is an amplifier, it will amplify both signal and noise. Definitely during the output of the amplifier, you will get minimum signal to noise ratio compared with input side. So as per the definition is represented, signal to noise ratio means signal power divided by noise power. If you want to maintain a good communication system, or if you want to get a good quality of the signal, each and every point of time or block, we have to maintain highest signal to noise ratio. Signal to noise ratio is normally expressed in terms of dB. So that also, if your two different equations are available, one is voltage equation, another one is power equation. Two equations are there. In the power equation, the signal to noise ratio represented in terms of dB, 10 log base 10, PS signal power divided by Pn noise power. Signal to noise ratio in dB in terms of voltage, given as signal to noise ratio equal to 20 log base 10. So Vs divided by Vn. So all the possible efforts are made to keep the signal to noise ratio as high as possible under all the operating condition. That is a minimum requirement in any communication system. We have to maintain highest signal to noise ratio at each and every point of time. So then noise factor. The noise factor of an amplifier or any network is defined in terms of signal input signal to noise ratio and output signal to noise ratio. So by using this particular factor, we are able to calculate what is the noise domination or noise introduced because of the amplifier alone. So we are applying the signal to amplifier, then you are getting the output. What is the noise contributed because of this amplifier? So that will be calculated by using noise factor. So the noise factor is equal to signal to noise ratio at the input divided by output. So input side, what is your signal to noise ratio, and output side, what is your signal to noise ratio, that will give a noise factor. So if you are substituting the corresponding values here, you will get a equation as PSI signal input power and PNI signal noise power input side, and PN not representing noise power output, and PS not representing, O representing output, S representing signal, P representing power. So then signal to noise ratio at the input will be always greater than the output, obviously, because if your signal is suppose 5 volt, due to this gain factor, suppose if it is 5 and 5, if you are multiplying, 25 will be the output. If it is a noise, similar manner it will amplify. Okay, it will be multiplied with 5. So that's why signal to noise ratio at the output is always lesser compared with input. So therefore the noise factor is to the measure the amount of noise added due to the amplifier. It will always be greater than 1. The ideal value of the noise factor is 1. If both the values are same, what will happen? You will get 1. That is the maximum value. Okay, that means the noise is almost 0. So that's why by using noise factor, we are able to calculate what is the noise added because of the amplifier. The noise factor will be expressed in terms of decibels, dB, that is called noise figure. So noise figure F dB equal to 10 log base 10 F. So the noise figure is equal to 10 log base 10 input signal to noise ratio divided by output signal to noise ratio. So the noise figure in dB, SNR input minus SNR output. The ideal value of the noise figure is 0. So that means if noise factor is 1, if the noise is 0, the noise figure will be 0. So if you are going to take a dB for 1, you will get 0. To improve the noise figure of the receiver, the device used for the amplifier and mixer stage must produce low noise. So we have to carefully select the devices to design a receiver. That is most important thing, to reduce the noise domination in the receiver. The diode and FET are preferred compared with transistor. So the diode and field effect transistors will reduce the noise level in the communication system because number of junctions are less in diode and field effect transistor. If number of junctions increases, the partition noise will increase. So the receiver can operate at low temperature. So the thermal noise domination is because of the temperature. So if the temperature is less, the noise generated internally will be reducing. Use high gain amplifier. All this will collectively improve the noise figure and factor at the receiver side. Now we are going to discuss about amplifier noise contribution in terms of noise factor F. What is the actual noise contributed by the amplifier? How to calculate it? That will be calculated by using the various formulas. Now you can see the first picture representing if the input signal is SIN. So power of input signal applying to the ideal noiseless amplifier, multiplying with the gain factor, what will happen? Output is G into PSI. Similar manner for noise. If it is noise, PNI is equal to KTB. So this KTB multiply with G, we will get PN0 is equal to GKTB. Okay. So now if the amplifier itself contributing the noise, that means noisy amplifier, because of improper selection of devices and also the temperature, the noise introduced in the amplifier will increase. In that particular situation, signal power PSI is equal to multiplied with gain GSI. So that means GPSI. Suppose if it is a noise, so KTB multiply with G and also a noise factor F. So the additional factor here they are provided as F. This is because of the noise introduced due to amplifier. So PNA is equal to FGKTB. So we have to calculate what is the F. Okay. So what is the noise power contributed because of the amplifier. Okay. So then we can start how to calculate this corresponding F or noise due to the amplifier. The total noise referred to the input of the amplifier is output divided by gain. You will get a input. So the output is PN0. Okay. So the Pn naught is the corresponding output divided by gain, you will get a input noise. So if it is a noisy amplifier, the same formula we are going to utilize, Pn naught divided by G, okay, gain. So that will give PNI total. Okay, the PNI total, why they are specified PNI total? The PNI total consists of source noise and also amplifier noise. So in this particular situation, you know the noise factor formula, output signal to noise ratio divided by input signal to noise ratio. Rearrange this parameter. Finally, you know that output power divided by input power is called gain. So gain G is equal to output divided by input. So that will be replaced here. So you will get Pn naught divided by G into Pni. So now rearranging this final equation, the Pn naught is equal to Fg Pni. So noise factor, gain factor multiplied with the input noise, the final output is Pn naught. So you know that the general formula Pni, the input noise, is equal to KTB or KT0B. T0 representing room temperature. Now we are going to rewrite Pn naught is equal to Fg KTB. We are going to replace this Pni by using this particular formula. So Fg KTB. So now substituting this particular final equation or output noise equation in this first equation. So Pni total equal to Pn naught divided by G. The final equation is FKT0B. This is the total noise. Okay. So the total noise because of the amplifier and also source. Now we have to calculate what is the noise contributed by only amplifier. Okay. Input source contributed is KT0B, and what the remaining noise obviously because of the amplifier. So the PNI total is equal to source contributed noise plus amplifier contributed noise. Then we know that PNI total we are already calculated here. Now we need only PNA. So the PNA is equal to total minus this source contributed noise. We will get PNA. So PNA equal to total minus PNI. Substitute both. We will get the amplifier noise power PNA equal to F minus 1 KT0B. So that means this is the expression for the noise contributed by an amplifier alone. If it is an ideal amplifier, your noise factor is 1, the PNA equal to 0. If it is an ideal amplifier. Otherwise, the corresponding noise domination will be there, or noise contribution is there because of the amplifier. That will be calculated by using PNA is equal to F minus 1 KT0B. Now similar manner, if n number of amplifiers are connected in cascade, what is the noise contribution because of the n number of amplifiers? In the previous slide we are discussed about what is the noise contribution of single amplifier. Now we are moving towards what is the noise contribution of cascade amplifiers, how to calculate it by using Friis formula. So it is necessary to see the effect of cascade connection of amplifiers. So the noise factor and noise temperature. The overall noise factor of such cascade connection can be determined as follows. Let the power gain of the two amplifiers are G1 and G2. Power gain of the amplifier G1 and G2, and noise factor is F1 and F2. The total noise power at the input of the first amplifier is given as. So here the total noise power at the input of the amplifier 1, PNI total, equal to F1 KT0B. So then what will be the output of the amplifier? Obviously multiplying with G1. So the Pn0 multiplying with G1, F1 KT0B. So now This will be the input of the next stage of amplifier. This is the noise due to your source plus amplifier 1. So similar manner, this amplifier 2 will add some more noise additionally with this particular output noise. So then what will be the total noise input to the amplifier 2? So the total noise at the input of the amplifier 2 is the first term representing output of the amplifier 1, G1, F1, K, T0, B. The second term representing noise because of the amplifier 2. So F2 minus 1 K T0 B. This entire value, if you are going to apply towards amplifier 2, definitely this will be multiplied with the gain factor of G2. So the Pn0 is equal to multiplying G2 multiply with total input of the amplifier 2. Then the final equation is Pn0 is equal to G1 G2 F1 K T0 B plus G2 F2 minus 1 K T0 B. The overall noise factor F is defined as follows. As per this particular block diagram, two amplifiers are available. So that's why the noise factor equation is total output divided by G1 G2 multiplying with Pni. So this formula already we are familiar in the previous derivation. You can see here Pn0 divided by G, because here only one amplifier is there. The total input noise is equal to total output divided by gain factor. Now in the Friis formula calculation, we have two amplifiers. That's why two gain factors are there, G1 and G2. Output divided by gain factor G1 and G2 and your input noise. So this is the corresponding noise factor calculation. Here we have to substitute this final equation. Pn0 is replaced here. Substituting that, then G1 is cancelled here and G2 is cancelled here and K T0 B commonly cancel. Then finally F is equal to F1 plus F2 minus 1 divided by G1. This is the formula applicable for cascade connection of two amplifiers. If you are connecting n number of amplifiers, then F is equal to F1 plus F2 minus 1 G1 plus F3 minus 1 G1 into G2 plus F4 minus 1 G1, G2, G3. Next factor F5 minus 1 G1, G2, G3, G4. So like that it will be extended. The above equation indicated that in cascade configuration, the first stage is most important stage in deciding the overall noise factor, because this F1 factor is very important, because based on this noise only it will be amplified next stage, and also the first factor is not divided to anything, but in the second factor divided by G1, the third factor is divided by G1 G2. So if you are keep on increasing the division factor, the domination of noise due to that particular amplifier will reduce. That's why approximately what they are specifying, F is approximately equal to F1. So then we have to apply the input signal carefully by calculating signal to noise ratio at the input side. You have to maintain the maximum signal to noise ratio, then only the noise factor will be less. So now the noise temperature. The next one is the same noise is represented in terms of temperature. So some particular situation like the equivalent noise temperature is used in dealing with UHF and microwave low noise antenna receiver or devices. In that particular situation, instead of calculating noise factor, the equivalent noise temperature calculation will be very easy. So that's why we are calculating equivalent noise temperature at the amplifier side at the frequency range of UHF and microwave frequency. We know that the noise at the input of the amplifier is given as PNA equal to KT equivalent B. The noise power due to the amplifier PNA equal to F minus 1 KT naught B. This is calculated in your previous slides. Single stage amplifier, what is the noise domination or noise contribution? So both are equated, then the common terms are removed. The final equation is T equivalent equal to F minus 1 T. This equation shows that T equivalent is just an alternative measure of F or noise factor. By using noise factor, we are able to calculate the equivalent noise temperature. Similar manner, this is extended to cascade connection of amplifiers also, the equivalent noise temperature. So you know that the equivalent noise temperature equation is F1 minus 1 into T. So similar manner, you know that the Friis formula is available. Subtract 1 from both sides, F minus 1, F minus 1. Now rearrange this equation, you know that F minus 1 T equivalent divided by T naught. Substitute this in your previous equation, T equivalent divided by T naught equal to T equivalent 1 divided by T naught plus T equivalent 2 divided by G1 into T naught and so on. Then T naught will be the common term, we are cancelling both the sides. T equivalent equal to T equivalent 1 plus T equivalent 2 divided by G1 plus T equivalent 3 divided by G1 into G2. So this is the equivalent noise temperature equation for the cascade connection of amplifiers. I think this particular video useful for you. If you like this video, comment, share, subscribe. Thank you all for watching this video. We will meet again with other video. Thank you.